Now we're not going to do a whole lot with Fisher projections. I'm not going to ask you to draw them. Think of Fisher projections, though, we do need to talk about them a little bit because we're going to use them when we talk about sugars. Is a two-dimensional representation of a three-dimensional molecule. What we're talking about is sugar molecules, all molecules are three-dimensional. And what this technique does, it gives us a way to look at molecules that's a little bit simplified, okay? So we're going to take this molecule, which the dashes normally mean that it looks like that, and the wedges would mean it looks like that. So these two things are coming out of the board, and these two carbons would be going back into the board, okay? That's kind of hard to draw all the time. So what we do is we draw it like this with a cross, and every time there's a cross, like this carbon is chiral, indicating there are 4 different things that are bonded to this carbon atom, okay? Are there 4 different things bonded to this carbon atom?
Yeah.
There's a hydrogen, there's a hydroxyl, there's this CH2OH down here, and then there's a carbonyl carbon up here, okay? The other thing that we do with Fisher projections is we put the most highly oxidized thing at the top. So here we have an aldehyde, and it goes at the top, okay? And you say, what difference does that make, Dr. Powell? Why are we doing this? Well, when we look at these isomers, these stereoisomers, look, here we have erythrose. Here we have our carbonyl carbon up here. And when we look at this, this is a chiral center right here. This is a chiral carbon. These two molecules have the same molecular formula, but look at what's different. Look at this carbon right here. This hydroxyl group, the position of it tells us whether it is L or D. When the hydroxyl that is furthest from the carbonyl carbon is on the left, it's an L form. When the hydroxyl that is furthest from the carbonyl is on the right, it's a D form.
Why is it D and not R? Good question.
They asked me in the last class too.
Well, you got L for left, why not have R for right?
Because it doesn't stand for left and right.
It should.
Do you really want to know?
Yeah.
Because most of these molecules will rotate light if you put them in solution and you shine light through them. Y'all know how about polarized sunglasses rotate light? These molecules rotate light. L means levorotary and D means dextrorotary. Left rotating and right rotating. You asked.
I know. That still doesn't make sense, but okay.
L means left, D means right. How's that? Just accept it. And because R is used for something else that we won't get to.
Well, they should use D for whatever R is used for.
That's right.
I don't make the stinking rules. I'm just telling you what they are, okay? Okay, look. How did we get L and D? That's the question. We look at the chiral carbon that's the furthest away from the carbonyl group. And if the hydroxyl is on the left, it's L. If the hydroxyl is on the right, it's D. Because all carbons that aren't carbonyl are hydroxyls in sugar molecules. Okay? Let's do a couple. Oh, first we got to decide, can these be superimposed or not? Are these stereoisomers enantiomers or not? How do you define if they're enantiomers or not? Is that carbon chiral? Are these mirror images of each other or not? Are these mirror images of each other?
No.
Yes. And is it carbon chiral? Yes. Are these mirror images? Yes. Is it chiral?
No.
No. So these are not enantiomers. These are not, because they're not chiral. Okay? Fair enough? Okay. Identify L or D. I'm going to help you do the one on A first, and then you guys are going to do B. Where's my carbonyl carbon?
It's on the right.
It's up here, right? So here's my carbonyl carbon. Where's my chiral carbon that's the furthest away?
It's on the right.
It's down here. This one's not chiral, right? So it's this one. Which side's the OH on?
Right.
On the right. So this is
D.
D. Okay? What about B? It's L, isn't it? Everybody sees that it's L? This carbon right here, right, it's the furthest away from this group, and it is over here, so it is L. Hey, we got them right. Woo!
Yay.
Who gives a rat's you know what about that? Because it seems like we're doing a whole lot of work to figure out if it's L or D, doesn't it? Do you care? You should. Your body cares. Okay? Anybody here take multivitamins? You ever read the label? You ever see L-ascorbic acid? You should. Does it have ascorbic acid in it? What's ascorbic acid? We know what ascorbic acid is?
I just feel like you're gonna tell
Who's
us.
got nutrition? Anybody take a nutrition class? Biology class? No? Y'all didn't learn about ascorbic acid? Learn about vitamin C?
Yes.
Ascorbic acid, vitamin C. L or D?
L.
It's L.
So,
It says it on the bottle.
L, so what do you-
You can't use D. Your body doesn't use D. So what happens to D? Well, ascorbic acid, your body takes and converts it to L. But for most things that are the wrong form, what does your body do with them? Peel it all out. Your body can't use it. It's like, oh, keep it all moving. Don't need that one. Why is it that way? Same reason you can't put your right hand in a left glove. Molecules work the same way on shape recognition, particularly enzymes. An enzyme recognizes a molecule by its shape. And if it's right-handed, and I go to shake your hand with my left hand, that's weird, isn't it?
yeah, you're on the back of my hand trying to shake.
Doesn't fit, does it? Don't work. So that's why it's important. And here's a very good picture to show you that. Look at the one on the left. Is that carbon in the middle chiral? Yes, it is. It's bonded to 4 different things, isn't it? Look at how it fits into that enzyme. Perfectly, right? The triangle, the circle, and the cube all line up. Would fit right in there. Look at the one on the right. It's the same molecule, right? It's the mirror image of it. But because this carbon's chiral, this is a non-superimposable mirror image of that. This one fits in the enzyme. This one does not. Now who cares? You still don't care, do you?
I never said I didn't.
Yeah, you did. You shook your head no. I saw it. Probably pretty important, right? It is very important, okay? This is how a lot of processes work in your body are on these enzymes, and molecular shape is extremely important. And simple differences like this determine, does this happen or not, okay? Here's another example. Here's L-DOPA and D-DOPA. It's a drug that's been developed to treat Parkinson's disease. It's converted to dopamine in the brain, okay? And it raises your serotonin level. Anybody that's ever had problems with depression knows about serotonin and sleep and all that kind of stuff, right? Serotonin is instrumental in your happiness, right? Okay. These two molecules look identical, don't they? Almost. They actually are chiral. They are non-superimposable mirror images. They're enantiomers of each other. Where this little star is right here, this carbon is a chiral carbon. It is bonded to 4 different things. And L-DOPA works in your brain, D-DOPA doesn't do anything. It will not bind to the right substrate, okay? So if I give you a whole bunch of D-DOPA, it's not gonna do anything for you. L-DOPA will do what? Make you happy. Better live
That's
through
what I-
chemistry. I don't have any of this. I imagine it's very expensive, okay? For most drugs, there's only one of the enantiomers, one of the images actually works. The other one doesn't fit into the enzyme, doesn't work at all, okay? Today, there's lots of research going into how do we separate these things out because they look very similar. How do we separate them? There are lots of guys that make a living figuring out ways to separate the two enantiomers from each other. It's often not very easy to do, okay? So, here we have 3 monosaccharides. We have glucose, galactose, and fructose. They're all D isomers, okay? D enantiomers. Why D? Because the hydroxyl group on the 5 carbon is on the right-hand side. Okay, fair enough? We're not going to draw these structures, okay? I do want you to be able to do this though. How many chiral carbons do we have here?
2.
There are 2, right? 1 and 2. Okay? Is it L or D?
L.
Why L?
Because it's on the level.
Because this is on the left. This is the furthest from this, so it is on the left. This is an L form. Okay? So, where do you find glucose? D-glucose is found in fruits, corn syrup, honey, lots of places. It's an aldohexose. It's an aldehyde, has 6 carbons. Once it's in your blood, it's also often called dextrose. So when you go see somebody in a hospital and they're on an IV drip, they'll often be on a 5% dextrose drip. Okay? That puts sugar into their blood so that they can actually maintain some basal metabolic function. Okay? Glucose is the building block of lots of sugars that we use. It is a monosaccharide that's used in sucrose, lactose, and maltose, which are disaccharides. It's also present in many polysaccharides like cellulose and glycogen. Fructose is found in what? Fruit. It's obtained from sucrose, which is a disaccharide. It is a ketohexose, so it's not an aldehyde anymore. It's now a ketone, and it also has 6 carbons, so it has the exact same molecular formula as glucose does, except that it's a ketone instead of an aldehyde. Okay? And because of that, it has a very sweet sensation to you. Fruit tastes very sweet to you, doesn't it?
Yeah.
Okay?
Sometimes. That's right.
Yeah, if it's supposed to taste sweet,
So for
right?
grapefruits.
I can't stand grapefruit. Okay, the sweet taste of honey comes from these. And the third monosaccharide we're going to talk about is galactose. It is an aldohexose as well. It's also C6H12O6. It's not found in nature free by itself. It only occurs in nature in a disaccharide, meaning 2 monosaccharides joined together, such as lactose. Where do you find lactose? Milk. Okay. Has a similar structure to glucose, except for the OH on the 4th carbon. It's on the opposite side. Okay. Hyperglycemia and hypoglycemia. Hyperglycemia means your blood sugar is too what? High. We often, if this happens often enough, we call this what? Diabetes. In South Georgia, they say you got the sugar.
From South Georgia.
Not South Georgia, South Louisiana. Sorry. In South Louisiana, they say you got the sugar. That means you're diabetic. And why do they say you got the sugar? Because your blood sugar is too high and you can't get it down. Why not? What's wrong with you?
Insulin.
You need some insulin. Your body isn't producing enough insulin. It can't break down the sugar in your body, okay? Some women become gestational diabetic. It's a temporary thing for most women when it happens. They don't process sugar well when they're pregnant. Sometimes it carries over afterwards. Most of the time it goes away. What does that lead to? What does gestational diabetes lead to? Anybody know?
Type 2.
Yeah, it can lead to type 2 diabetes, but it doesn't have to. But what does it lead to in the infant when you're gestational diabetic? Very large birth weights. Most babies that are over 10 pounds, or not all, but a lot, are because the mom was gestational diabetic. My first child was 10 pounds, 8 ounces. I did not give birth to this child, thank God. And they have this switch. Anybody that's ever been pregnant, and they make you take the time sugar thing, you did it, right? You drink this awful tasting stuff, and then they check your blood sugar over time to see what happens, right? If you're hypoglycemic, what's the problem? Blood sugar's too low. Now, I think that hypoglycemia happens more as you get older because you tend to process sugar a little bit differently. I know when I exercise, I have to be real careful about what I eat and how much of it I eat leading up to exercise, because when I go exercise, I can feel my blood sugar get really low sometimes. How do you fix that? Eat an orange, piece of candy, piece of hard candy or something like that. Drink some Gatorade, something sweet will get your blood sugar back up, right? And it feels, having low blood sugar feels awful. So either one is not good for you. We're not going to draw Fisher projections.
We have to do something with them.
No, you don't.